All right, today we're going to start chapter 4, some additional ideas on taking derivatives, specifically for composite functions today. Remember, a composite function is one where you have a function inside of another function, where the output of that first function is used as the input for the second function. Okay, so typically we think about it as y is equal to f of g of x. So in this case, g is the inner function and f is the outer function. So one of the things that you're frequently going to have to do is spend a little bit of time rewriting the function as a composite function. So for example, if we take a look at this first one, if we have 1 over 2x plus 3 is equal to y, how can we write that in composite form? Yes. So it'd be y is equal to 2x plus 3 quantity to the negative 1 power. So now we have an inside function of 2x plus 3 and an outside function of a power of negative 1. Some of them are as simple as number 2, where all you really have to do is add a set of parentheses to kind of see that it's a composite function. This is y is equal to the tangent of 5x. And some of them really are just that simple. What about y is equal to sine cubed of x?
You would say y is equal to sine of x quantity cubed.
Exactly right. Y is equal to sine of x quantity cubed. And then sometimes it's not written as a power, sometimes it is a radical, but we can rewrite those pretty easily. This would be y is equal to 4x squared minus 8x to the 1/2 power. Notice that none of those, other than the first one, do we know how to take the derivative. I suppose we could do sine cubed of x by doing sine of x times sine of x times sine of x and doing a 3-part product rule. And number 1, we could do that by the quotient rule. But number 2 and number 4, we absolutely don't have a way to do that just yet. Okay? So the rule that we have that helps us with all of these is the chain rule. So before we get into what the chain rule actually says, let me show you an example. So let's let y be equal to x cubed plus 4 quantity squared. Now, with what we know right now, the only way that we could take the derivative of that would be to go ahead and expand that. That is, multiply the x cubed plus 4 times the x cubed plus 4. That would give us x to the 6 plus 8x cubed plus 16. And then we could take the derivative of that, which would be 6x to the 5th plus 24x squared, which, notice, you could factor out a 3x squared, and it'd be 3x squared times 2x cubed plus 8. Everybody good with that? Okay, and that would be fine if it's only squared. But what if that was x cubed plus 4 raised to the 17th power? You would do what? Which wouldn't be helpful because it's not a numeric derivative. Thanks for playing. We have some lovely party gifts for you. Okay? The parting gift? I give him a pencil of his very own. Excellent, excellent. I loaned a pencil to one of my geometry students the other day, and he's like, "You don't have a mechanical one?" And I was like, "Man." It's like, have you ever heard of the phrase "beggars can't be choosers"? And he's like, no.
That explains it.
And then he was like, what does it mean? Never mind.
Some people say, I can't use a real pencil unless I'm a mechanical pencil. I mean, I get the appeal, but I like the woodenness of the pencil.
So if we had tried to take the derivative in its original form by just doing the power rule, we would have moved the 2 in front and had 2 times x cubed plus 4 to the first power, which would be 2x cubed plus 8. Notice, is that the correct derivative?
It's kind of close.
It has some parts that are alike, right? It has this 2x cubed plus 8 that we do have. What's it missing?
3x squared.
The 3x squared.
Get it?
Pardon?
You bring the 3 down from the x cubed and the 3x then squared.
So what are you doing with this inside part then?
You find the derivative of the inside.
We're taking the derivative of the inside part. So we can treat it like we normally would, but then we have to multiply it by the derivative of the inside part in order to get the correct derivative. Okay?
He's going to make it so complicated.
Pardon?
He's going to make it super complicated.
No? So if y equals f of u is a differentiable function of u, and u is equal to g of x is a differentiable function of x, then y equals f of g of x is differentiable, and in Newton's notation, f prime dy dx is equal to f prime of g of x times g prime of x. The derivative of the outside function, leaving the inside function alone for the time being, times the derivative of the inside function. In Leibniz notation, that's dy dx is equal to dy du times du dx. And there are some times when Leibniz notation is a lot easier. We'll get to that. Yep, it doesn't look like it. It looks like it would be worse. There are occasions where it's like, because of the way that the problem is presented, it's much easier to do it in Leibniz notation. So an example of one where doing this by expansion would be just nutty. We want the derivative with respect to x of x squared plus 5x minus 9 raised to the 24th power.
You don't expand that easily?
Not easily. You could expand it.
You could give it to
Earthon would do it.
What's called detention.
But doing this by the chain rule is pretty simple. We deal with the outside part, leaving the inside part alone. So that's going to be 24 times x squared plus 5x minus 9 raised to the 23rd power. That's the outside part taken care of. Then we need to multiply that times the derivative of the inside part. The derivative of x squared plus 5x minus 9 is pretty simple. It's 2x plus 5.
I have a question.
I have an answer.
I wrote 24x squared plus 120x minus 216.
That would be completely and totally in all other ways wrong.
Really?
Yes.
I said raised quantity raised to the 23rd times.
Nope. You cannot distribute this 24 across here because this is being raised to the 9th power first.
Oh,
Only if the 24 was to the 9th power also could you distribute the 24.
My ancient
Emily? Anemone? Okay. And typically, people will leave it like this. They might multiply the 24. Now, if you want to multiply the 24 times the 2x plus 5, okay, that's fine. But we usually don't bother, frankly, because having it in factored form is more useful generally for what we're going to use the derivative for than having it in some other form.
Plug and chug.
Okay? I don't know what you're babbling about.
Is we're gonna plug stuff into it, right?
But you've got x there. What are you going to do with your x's?
If, for example, we were interested in finding where you had horizontal tangents,
Yeah.
it would be more useful to have it in factored form. Okay? So there are all kinds of different things that teachers will talk to their students about when they're doing the chain rule. Some liken it to peeling an onion a layer at a time. You take care of the outer layer, you leave the next layer alone, then you do the next layer. I prefer to think of it as an M&M, which has a hard candy shell. You put it in your mouth and don't chew it. The outside part dissolves, leaving the inside part, and then the inside part dissolves. However you want to think about it is fine with me.
Can you just think about it in mathematical terms?
Sometimes we have to rewrite this. Sometimes we have to rewrite them. What?
I'm fainting right now
Why are you fainting?
because
He's bleeding.
yeah, I'm actually super bleeding. I need to go home. I had a gruesome injury.
So I'm going to rewrite this as negative 3 times 4x minus 7 raised to the negative 5th power before trying to take the derivative of this. Now, could we do this using the quotient rule? Yes, but you would still have to use the chain rule when you take the derivative of the denominator.
No, thank you.
So, the derivative now, we'll just leave the inside part alone, so I'm just dealing with the outside power rule part. So that'll be 15 times, leave the inside alone, 4x minus 7, raised to the negative, what power will that be?
6.
Negative 6.
I caught that on the test.
Excellent. Times the derivative of the inner part, which is 4. And since those are both constants, we'll just go ahead and multiply them together. We'll have 60 times 4x minus 7 to the negative 6th power.
So you just multiplied your first constant by the 4.
Yes. Because multiplication is commutative and associative. I can rearrange it any way I like, and I can group them any way I like. I am the god of this problem. Actually, not really.
We could
I
make
don't-
like a speed date.
I don't have absolute power, but I have almost unlimited power within certain constraints.
That sounds.
They need like a game of life, and you like end up being like a different math, like function, operation, and you're in like multiplication. I'm commutative and associative.
That sounds like
And then,
communism
like,
to me.
Interesting.
That's a proud American.
That sounded better. In my head.
All right, so for this next one, how can we rewrite this so that we don't have to use the quotient rule on?
6 times 4x squared minus 9 to the negative 3.
No, it would be 6 times 4x squared minus 9 to the 1/3.
Well, you're both wrong.
Negative 1/3.
There we go, the negative 1/3 power. Between the two of you, you had it right.
Stupid minds make a semi-right idea.
So then the derivative, y prime, I'll multiply the 6 times the negative 1/3, and that'll be negative 2, times 4x squared minus 9. To what power?
That would be
Isn't it
2 negative 4/3.
To the negative 4/3 power.
Where'd you get the negative 4?
Because it's 1.
Negative 1/3 minus 1 is negative 4/3.
Oh.
Times the derivative of the inside part, which is
8x.
8x. And again, since it's a simple expression at the beginning and at the end, we'll usually go ahead and combine those. So make negative 16x times 4x squared minus 9 to the negative 4/3 power. Or, occasionally, if this is a multiple choice question, since it was given in radical form,
Put it back
it's
down.
common to put it back into radical form.
So would it be the 4/3 root?
Well, it would be negative 16x in the numerator over the cube root of 4x squared minus 9
Raised to the 4.
raised to the 4th power.
That's.
Because whenever it's 1/2, you're raising it to the 1 power.
Yeah, I know why. It's just,
When it's 1/2 what?
Let's say it's 4x squared minus 9, then all that's raised to the 1/2. Whenever you put it back down into the denominator, it's still being raised to the 1 power. It's just you don't write it. I'm explaining it to Lance.
I don't know what you're talking about. What's raised to the 1
No,
power?
I'm just giving an example.
Okay.
I need to go to chapel, Mr. Davis.
Okay.
So I will watch the video notes. I will like and subscribe.
How are you doing?
I'm playing today. Yeah, you're gonna watch me.
All right.
And listen to me.
So for this one, this will be the derivative with respect to x of cosine of x to the 1/2 power.
Facts.
So we'll deal with the outside part, 1/2 of cosine of x
Mr. Davis.
to the negative 1/2, goodbye, times the derivative of cosine of x, which is negative sine of x. And then again, typically we'll rewrite this so that it's back in radical form. So that would be negative sine of x over 2 square root of cosine of x.
So every time we need to rewrite it, or we can just let that one.
We can just do what? I'm sorry?
So every time we need to rewrite it, like the final step, right?
You don't absolutely have to. I'm just telling you that if it's a good habit. But if I was doing this on the AP exam and this was a free response question, I would leave it here. I wouldn't do any more. Because the only thing that can happen is something can go wrong. And I'm going to get full credit for this as an answer. If it's a multiple choice question, it's likely that that choice is not there, but that this one is. So that's why it's a good habit to practice it. But then when if it's on a test, whether it's mine or the AP exam, you're welcome to leave it like this. Okay? So far, all of our outer functions have been power functions once we've rewritten them. But in some cases, the outer function is something other than a power function. Like this one, for example, where y is equal to the secant of 6x. The outer function is the secant function. So we'll take the derivative of the outer function, carrying the inner function with us. The derivative of secant is secant tangent. So that would be secant of 6x tangent of 6x. Times the derivative of 6x, which is just 6. And again, it's usually standard to write any coefficients in the front of the expression. So it's 6 secant of 6x, tangent of 6x. Then remember that for one like this, how can we rewrite that so that it's in composite form? Oh, before we're taking the derivative, we're just rewriting it. It's tangent of x raised to the 5th power. I think you were already thinking that. So now we'll take the derivative, f prime of x, and that'll be 5 tangent of x to the 4th times the derivative of tangent of x, which is secant squared of x. Occasionally, we'll have a function inside of another function, inside of a third function. And that's the case here. Notice there's no parentheses telling you that, but we could rewrite this as f of t is equal to the cosecant of 7t raised to the third power. So now that when we take the derivative, we'll have f prime of t is equal to 3 times the cosecant of 7t quantity squared times, now we'll move the next layer in, which was the cosine, or excuse me, the cosecant. The derivative of cosecant is negative cosecant cotangent. So it would be negative cosecant. We're still going to keep the inside part, 7t times cotangent of 7t times the derivative of the very innermost part, which was 7t, is just 7. So then my constant multiples, I've got 3 and a negative 1 and a 7, so that's negative 21. And I've got cosecant squared of 7t times cosecant of 7t, so that's cosecant cubed of 7t times the cotangent of 7t. And this is pretty typical of derivatives of tangent and secant and cosecant. They tend to get just uglier the more you take the derivatives. They don't get nicer. Okay? All right, let's go on to the last page. So for these, we're not only going to be using the chain rule, but since we have two things that are multiplied together, we'll also be using the product rule, or in this case, the quotient rule. Or we can rewrite it as a product. We'll take a look at both and see which one we prefer. So here, again, doing a little bit of rewriting first, we'll have y is equal to x cubed times 4 minus x squared to the 1/2 power. So when we take the derivative, dy dx, we'll keep the first factor, x cubed, times the derivative of the second factor. And to take the derivative of this second factor, we'll have to use the chain rule. So that'll be 1/2 of 4 minus x squared raised to the negative 1/2. So we've done the outer part, times the derivative of the inner part, which is negative 2x, plus, now we'll keep the second factor, 4 minus x squared to the 1/2 power, times the derivative of the first function, which is first factor, which is 3x squared. I'm going to clean up the first one a little bit, and then I'm going to factor it so they get a nicer expression at the end. So the 2 times the negative 2 just leaves me with a negative 1. So I've got negative x times x cubed is x to the 4th power times 4 minus x squared to the negative 1/2 plus 3x squared times 4 minus x squared to the 1/2 power. Notice for both of these, I can factor out an x squared. And you may notice that I have these two expressions, the 4 minus x squared to the negative 1/2 and the 4 minus x squared to the positive 1/2. Well, in order to think about factoring those, let's go back to factoring out the x squared. We factored out the lower common factor, right? x squared is less than x to the fourth. So here we're going to factor out the lower one. So that'll be the 4 minus x squared to the negative 1/2. When we do that, if we factor all of that out of this first term, from the x to the fourth, factoring out an x squared leaves us with an x squared because we're subtracting the exponents. When we factor out the 4 minus x squared to the negative 1/2, that just leaves 1. So I don't need to bother writing that. Plus, if I factor an x squared out of 3x squared, I get 3. And this is the part where students occasionally are unhappy about it, but just like we did here, when we factored an x squared out of x to the fourth, we just subtracted the exponents. We're going to do the same thing here. When we factor a 4 minus x squared to the negative 1/2 out of 4 minus x squared to the 1/2, we subtract the exponents. And something really cool happens. 1/2 minus negative 1/2 is 1. So that's going to be 3 times 4 minus x squared with no exponent on it at all. So now this will be x squared times 4 minus x squared to the negative 1/2 power times, well, let's see, that's going to be an x squared minus 3x squared and plus 12, so I'm going to say it's 12 minus 2x squared. So now I have that in factored form, which again is much preferable, especially if we're looking for where the derivative is 0. Because we're going to find that when the derivative is 0, you have a horizontal tangent line. That's a potential place for my graph to turn around and go the other direction. Much like when we talked about velocity, if the velocity is 0, you have at least the potential for the car to change directions at that point. It's not absolutely certain, but it's certainly the potential for that. All right, let's take a look at this one. I think this is the last one, yes? Thank you. So let's look at doing this by rewriting it in a form where we're going to use the product rule. And then let's also do it in a form where we use the quotient rule, and let's see which one we prefer. So, to do the product rule, I would rewrite this as f of x is equal to x times x squared plus 9 to the negative 1/3. So the derivative, f prime of x, we'll keep the first factor times the derivative of the second, so that'll be a negative 1/3 times x squared plus 9 to the negative 4/3 times the derivative of the inner part of that composite function, so times 2x, plus x squared plus 9 to the negative 1/3 times the derivative of the first function, which is just going to be times 1. So let's see. If I multiply the x, the negative 1/3 times the 2x, that's going to be what? Negative 2x squared over 3, or negative 2/3 x squared, times x squared plus 9 to the negative 4/3 plus x squared plus 9 to the negative 1/3. Again, simplifying this completely, we would like to factor out what we can. And again, we have x squared plus 9 and an x squared plus 9 to different powers. I'll factor out the least power, which is negative 4/3. So this is going to be x squared plus 9 to the negative 4/3 times, I'll be left with negative 2/3 x squared plus, when I factored this out, negative 1/3 minus negative 4/3. Hey, that's really nice. It's 1 again. This happens all the time. So that's just going to be x squared plus 9. So we end up with x squared plus 9 to the negative 4/3 times 1/3 x squared plus 9. Now, go ahead.
So that's it, right?
Yeah.
So I just leave there and I don't need to rewrite it. Because you have the negative 4/3.
Some people will write that with the 4/3 power in the denominator so that there's not a negative exponent. And there's something to be said for doing that. I'm okay with it either way.
Okay. So
But
if in the quiz or task I leave like this way, it's okay, right?
yes,
Okay.
but it's not wrong if you rewrite that.
Okay.
Now, real quick, let's look at, well, what would have happened if we had rewritten it in a way so that we had to use the quotient rule? I think that you're going to find that you're not going to like it as much. This would be x over x squared plus 9 to the 1/3 power. I think simplifying it is going to be a lot harder on this. So the derivative, we would take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which would be 1/3 x squared plus 9 to the negative 2/3 times 2x all over x squared plus 9 to the 2/3 power. Now let's see if we can clean that up a little bit. Not much we can do with this first part in the numerator. That's just going to be x squared plus 9 minus, over here, I'm going to have 2/3 x squared times x squared plus 9 to the negative 2/3 all over x squared plus 9 to the 2/3 power. Looks pretty ugly. In order to simplify that further, and you may notice that it's like some of this looks surprisingly familiar. The x squared plus 9 minus 2/3 x squared. It looks pretty similar. Oh, I left this. This was to the 1/3 power. I left that off. Sorry. This is a complex fraction because of the negative power here. What we would need to do is, get some more real estate here, is multiply this by x squared plus 9 to the 2/3 power over x squared plus 9 to the 2/3 power. When we do that, the x squared plus 9 to the 1/3 times x squared plus 9 to the 2/3 is x squared plus 9 to the 3/3, which is just x squared plus 9. Minus When we multiply these two together, the x squared plus 9 to the negative 2/3 times the x squared plus 9 to the 2/3 will cancel out entirely. So it'd be 2/3 x squared over x squared plus 9 to the 4/3 power. Then grouping the like terms in the numerator, we've got 1/3 x squared plus 9 over x squared plus 9 to the 4/3 power, which is precisely what we had over here. Do you have a preference on that?
No.
I don't have a strong preference. I slightly prefer the product rule,
Yes.
but it's not terrible the other way.
It's terrible. It's easy to like make a mistake.
Yeah, and you have to remember to clear the complex fraction in order to simplify it. Now, on the other hand, over here, you have to remember how to factor out something to an odd, sort of weird power. Okay,
It's really easy to make a mistake because you need to check every step is correct.
that's true.